Okay, this is the last lecture of week 3, color flow imaging. Color flow imaging uses pulse wave Doppler to obtain Doppler shift information, okay, which is then color coded and superimposed on the anatomical display. So shifted echoes come back and they're received and stored in a certain memory location. And non-shifted echoes come back from grayscale, and they're also stored. So the shifted and non-stored, non-shifted echoes represent flow and anatomy. So the way color works, it's basically color-coded pulse wave Doppler information. Instead of assigning a positive or negative value on a spectral display, positive and negative is superimposed on the anatomical display with a color. And the processing chip that allows color to do this is called autocorrelation. So color uses a technique called autocorrelation to process this information. So there's 3 components to color. The hue is the color that is perceived by the viewer. The saturation is just like this picture over here. It's the amount of hue present in a mix of white. Brighter, lighter shades, and this is relevant to color, brighter, lighter shades indicate faster flow. Okay, so the brighter, lighter ones are the faster. This would be the faster flow here. And the deeper, darker shades are the slower flow. So if it's a deep, dark shade of red, it's slow. If it's a lighter, brighter shade of red, it would be fast, or blue, or whatever color assignment we decide to assign to our color map. And luminance is the brightness of the hue and saturation. It's how bright the actual image is, kind of like the amplitude. So what are some advantages and disadvantages of color? Well, color is able to detect if there actually is flow. We can tell the direction of flow with color. We can get a qualitative analysis of the speed, like we just mentioned in the previous slide. Lighter, brighter is faster, and deeper, darker is slower. So it's a qualitative analysis. That means we can look at it and go, yeah, there's fast flow there, or there's slow flow, but we can't put a number on it. That's what qualitative means. And we can tell the characteristics like turbulent, laminar. That's all in chapter 18, which we'll get into a lot deeper in chapter 18 when we do that in vascular. Some disadvantages. Decreased frame rates. Again, anything that takes a lot of time is going to decrease our frame rates and our temporal resolution. So color uses a lot of packets, anywhere from 100 to 400 packets. So that's going to take time to process that information. Color displays mean, average Doppler shifts, and again, they're color coded. So there's different variations and brightness to those images. Again, darker, there's a couple of deep dark shades that would indicate slow. And like Doppler, it is also angle dependent, but not as angle dependent. We just want to avoid 90 degrees because the cosine is 0 and we would not pick up any flow. And one of the major disadvantages of color is that it cannot pick up flow rates below 6 centimeters per second. It's too slow. So that's the major disadvantage to color flow imaging. So we have another type of color that we use for very slow flow. And it can also be considered a disadvantage to be qualitative versus quantitative. So velocity maps. There's two different kinds of maps. We have velocity and variance. So velocity maps have 2 color assignments. The color on the top of the map represents the positive shift, always. Let me change the color here. Okay, so whatever color assignment is at the top is always positive, and the color assignment at the bottom is always negative. Okay, velocity maps will give us information about flow and direction. So if you look at this map, the red color, the lighter, brighter flows would be faster flow, and the deeper, darker would be slower flow. And if it was red, it would be coming towards the transducer because that's a positive color assignment. Same thing now with the blue. The deeper, darker would be the slower flow. The light blues to almost green would be faster flow. And if it's filling in blue at all, that means it's going away from the transducer. And we would have to interpret that information as to whether or not that's normal for that vessel, meaning is it antegrade or retrograde? Again, this is a color map here, so I'm going to let you know that this is a carotid artery. So flow in the carotid artery is supposed to be going towards the head. So let's look at our display here and see if that actually is happening. First of all, we look at the tilt of the color box. It's obviously coming in a direction like this. So our color beams are coming in like this. Because remember, it has multiple beams for every single scan line, but I'm just drawing in a few of them so you see what I mean by the tilt. So again, this is the viewer. So if our eyes were over here, this is the direction in which our transducer is looking at the flow. And if it is in fact going towards the head in this direction, we should be receiving then a positive shift. So we look at the color that's being filled in this vessel, which happens to be red, and red is assigned to the positive color assignment. So therefore, we do have antegrade flow in this carotid artery. Now, a variance map is similar to the velocity map, except it has four colors. What it does is it divides the color map like this. So we have a left side and a right side. This is still positive if it's on the top, and this is still negative. But the left color on the left side, if it shows up just red or blue, that means there's laminar flow, which is just a very normal type of flow in a vessel where all red blood cells are traveling in a uniform direction in a uniform manner. Whereas if it shows up on the right side of the map, whether it's the top or the bottom, that just tells us whether it's positive or negative. But the right side, the lighter shades, the yellows and the blues, tell us if it's turbulent, disturbed flow. So that's basically how a variance map works. It has four color assignments. And just think of left laminar, which is what we're looking for, normal flow without disturbance. And this is a variance map showing a leaking valve in a heart. This is a dog's heart, and there's a regurgitation jet, which you can see right here. This is a large regurg, which means it's reversing and it shouldn't be. And then there's one on the other side. So this poor dog has pretty leaky valves. So here's another jet. So this is what a variance map would look like. You see these really light, bright shades. That's very turbulent flow. Whereas the deep dark blues and the regular reds, that's a very normal flow pattern. Power Doppler is not really a real Doppler, but it's what we use when we're trying to pick up really slow flow. So you need to know that this button can also be referred to as color power, energy mode, or color angio. Again, you'd have to look at your machine and see what the manufacturer decided to call it, but they're all the same exact thing. So what power mode does is it estimates the total strength of each signal within the gated region. The strength of this shift is determined by the concentration of red blood cells. that are moving within the gate. The amplitude of the reflection is directly related to the number of moving red blood cells. So the brighter it is, the darker it is there, that means there are more red blood cells in that particular area. It has nothing to do with velocity. In fact, power Doppler is very limited. The only thing we can tell with power Doppler is there flow? And it's very sensitive to super slow flow. And is there a lot of flow there? And let me show you the picture. See where it's this, there's no, there should be sort of a map, but there's no directional information. There's no information other than is their flow. So these lighter areas here are real bright areas. That means there are more red blood cells in those particular areas. Whereas on the edges, the darker shades there indicate that there's not very many red blood cells or a very low concentration. So all that you can tell with power Doppler is that there is flow and there's either a lot of red blood cells in an area or very few. So advantages, it's not angle dependent. There's no aliasing. These seem kind of silly because we don't use it to detect anything other than flow. So the only major advantage it really has over all the others is better sensitivity to very, very slow flow. So better sensitivity to slow flow rates. That's pretty much all it can do. Disadvantage, well, everything else. It doesn't tell us directional information. We can't get speed and we can't get characteristics. We can only get concentration, okay? Concentration, and it's very sensitive to picking up all red blood cells. So that's the reason we would choose power Doppler over color, because color is limited to anything above 6 centimeters per second. Below that, we wouldn't be able to use regular color to pick that up. So that's the only use for power Dopplers. If we want to see if there's flow, we're going to use this. Okay? So this was a short presentation. Just a couple other things about optimizing the color Doppler image, which we kind of already did in some of the previous lectures. If you have color aliasing, what they're going to do in the registry is show you a picture like this and ask you how you can fix it. Well, the first thing you should notice is the scale. Let me get a white here. The scale is set at 10.5 centimeters per second on the positive and the negative, which is very, very slow. So what that means is anything traveling faster than 10 is going to wrap around to the other side and pick up those color velocities. See the light blue? The light blue is being picked up here because the color map is actually aliasing. So this is what aliasing looks like in color. Now, how do you fix color aliasing? The same way you fix it with pulse wave Doppler. What we want to do is increase the PRF. If you increase your PRF, you're also increasing your velocity scale. So if this scale is set at 10 and we increase the velocity scale, say to 50, now most of this vessel should fill in one color, and it should fill in mostly red. So by bumping up the scale, it's going to now fill in red with just maybe a little bit of aliasing, because there's probably only a few red blood cells that are traveling faster than the 50. So if anything's traveling faster than the scale set on the color map, it's going to wrap around to the opposite color. And that's why you get these little areas of color aliasing. But what we don't want is the entire vessel aliasing, because then we can't tell directional flow at all. We can't tell whether that's red or blue or what direction it's going. So the first thing, again, you look at is this color map and make sure it's set at least 40 for an artery. Now for a vein, it can be under 40, but at least 40 for an artery. And that's the first thing you're going to do. So the rest shows you a picture like this and says, you know, how do you fix that? And there's going to be an actual panel of controls that you're able to click with a mouse and make the adjustments. So when we have color bleed, or what they refer to as ghosting artifact, that's when there appears to be color coming outside of the walls of the vessel. If that's the case, our wall filter is set too low. So to fix this, we need to filter out some of the vibrating wall motion that's showing up on the outside of the wall. So to fix color bleed or ghosting, you would look for the wall filter control, and you would increase that. We'd increase it just enough to clean up this outside flow. But we don't want to increase it so much that the flow doesn't touch the walls. We don't want it so that it's just in the center like this, and then you have void areas on the walls. If you have void areas along the walls, then your wall filter is set too high. So we need just the right setting. Now color confetti, this is different from the wall filter. This is the result of the Doppler, or the color gain rather, I should say, when we're using color. The color gain is set too high. So you'll have a control on your machine that says grayscale gain. You'll have one that says Doppler gain and one that says color gain. So it's the color gain. You want to turn down your color gain to fix this. Now, I don't know what kind of pictures are going to show up on your registry, but they are definitely going to ask you color and Doppler control questions and show you pictures, and they want you to correct them. So this one, you would take your color gain and you would turn it down to get rid of all that confetti on the outside. And this one is the result of a 90-degree angle. So what we want to do here, if you're getting a 90-degree angle and you're showing both red and blue, if you want to be able to tell directional information, you're going to have to give that color box a tilt to it. Now you can send it in this way, and if this is the carotid, we're expecting to get a negative shift, and that would fill in red if it was negative. That's one option to avoid 90, or we can choose to send in the beam this direction. It really doesn't matter as long as we understand how to read the color map and we understand what direction it's supposed to be flowing. So again, if it's supposed to be flowing this way and we choose to send in our beam in this direction, then we're expecting to get blue if there's antegrade flow. And you would have to know what vessel this is. See, I know this is the carotid. I don't expect you to know that at this point. So once we get into that and vascular, you'll know a little bit more about what's normal for a vessel. But if you know the name of the vessel and you know whether it's an artery or a vein, arteries are going to flow away from the heart towards tissue, and veins are going to go from the tissue back to the heart. So that's the main thing you need to know in this class at this point. And this is a protractor that helps you to eyeball angles. Sometimes it's hard to eyeball angles. That's why we have the angle correct on our systems. So if you're looking at this, and it's kind of hard to see, you've got, it looks like this, and then the flow is like that. It almost looks like a 90-degree angle. There's a slight tilt. Let me redraw that. So if we're looking at the part of the vessel here, and our beam's coming in like this, and our vessel's like this, we have a very slight angle. So we would use our angle correct, which works just like a protractor, and we'd be able to see the angles. If our vessel is lined up like this, and we have just a very slight angle, okay, I'm not good at drawing that, you can see that that's probably like an 80-degree angle here, which is not a desirable angle, right? We want something that's 60. So we would have to give our vessel more of a tilt, or our Doppler beam, either one, because what we're trying to do is get the angle of the flow to the beam at something like 60. So we would want to send in our beam at a sharper angle here, creating more of a 60-degree angle like that. Okay? So luckily we have sort of a built-in protractor, a little angle guide. So when you send in your beam, what you normally see is the beam, the gate, and then the guide. The guide, or the angle correct, is the line. Now this is obviously a poor angle here. This is like 90 degrees, so we want to avoid that. So color is somewhat angle dependent. It doesn't necessarily have to be 60, but it can't be 90 or we won't be able to pick anything up. Okay, so that's the end of color. So color is very similar to pulse wave. It's just color coded and then superimposed on the actual anatomical display.